Hello, students and parents, if you're watching this video. The purpose of this video is to do a reteach for our transformations test. So, if you're watching this, you probably want to score a little bit higher. This is for everybody who scored from 0 to 99. It's not just for students who failed, it's for everybody who wants to do better, which should be everybody. Okay. So, this is our little transformation reteach ticket, as you see right down here. And the idea here is that this form or paper you need to hand to Miss Gray, to Miss Hill, to Mr. Latta, or myself, or Miss Kano, or Miss Alanis. And so if you hand it to them, that is proof that you have done what you needed to do to prepare for your retest so that you can score higher. We don't want to just retest you for the kicks and giggles of it. We want you to actually watch this video, relearn the material. This video will be longer, but it is to show us that you learned and to show yourself that you learned, okay? There's also going to be weird little things throughout to prove to the teachers that you learned and didn't just copy from a friend or get all the answers from your parents or friends in general. So I have a whiteboard here, and 6 times in this video, I'm going to say, hey, draw something crazy like a Dallas Cowboy star. Or I might say, draw a Philadelphia Eagle. Whatever it is I say draw, I might do an example of it. I'm gonna ask you to draw it somewhere. You do that, and when we check your paper, that's how we'll know. So let's jump straight into it. Transformations reteach ticket. Your test that you just took, there was 6 styles of problems. We had slope, functions from the past. We had dilations, reflections, translations, and rotations. It was 10 problems, and your retest will be similar. And you will see problems about slope, functions, and the 4 transformations. So, reminder what slope is. Slope, and right here on your paper right now, these are all the answers, ladies and gents. Slope is, oh my goodness, that was ugly. Slope is the change in y, okay, over the change in x. You should be writing on your paper right now, ladies and gents. That's what slope is. When I ask you what slope is, Ms. Gray asks you, Ms. Hill asks you, you should say slope is the change in y over the change in x. It's steepness of like a mountain or hill. So if I were to climb up a mountain, see if you can see that. If I were to climb up a mountain here, that mountain has steepness. A hill has steepness. Now, when you're fat and out of shape like Mr. Heiston, you breathe really hard when there's a lot of slope because it's hard to climb up a mountain with a lot of steepness. Slope is how we calculate that. We're going to find the vertical change, the change in y, over the change in x, the horizontal change. Now, um, here you have 2 pictures of graphs. I'm sorry, of tables, and you need to calculate the slope from those or be able to. And right here it says if the slope line goes through the blank, it is blank. Our blank here is origin. If it goes through the origin, it is proportional. If it doesn't go through the origin, it isn't, or it is not proportional, or you could just say call it non-proportion. Bam. So that's what you need to know about slope. And when we say it goes to the origin, we know on a graph that would be 0, 0. That's also the center of a graph. I'm about to draw it here. This would be the origin, 0, 0. On this table here, you'll see 0, 0. That means this table on the left is proportional, and this table on the right is non-proportional. That is what you'll need to know for your slope review. Now, right here where my mouse is, and I'll draw it with my pen as best as I can, I need you to write the word eagle. Ooh, this is hard with a mouse. I mean, without a mouse, I'm writing with a little touchpad. So you can write the word eagles or draw the word eagles. That lets us know that you saw this section on slope. Now, we're going to go to this function section. Functions. For every x, there is one y. In class, we talked about relationships. That Mr. Heisen is married, right? I am a committed husband. So for me, there's one woman for me. For one Mr. Heisen, there's one woman for me. Okay, for every X, there's one Y. In a committed relationship, it's faithful, it's one-to-one relationship. I'm not cheating, and you never should either. But that's what a function is. You can also think of a vending machine. When you press the button, one soda or one snack should come out. If you press the button and multiple snacks come out, it's not a function. It's not a working, healthy relationship. And so for every X, there's one Y. When you look at these examples here, on your paper, I need you to circle the ones that are functions. Now, when you see it as a mapping diagram, do you see how this 3 is dating 2 and is also dating 6 is going to two different people? That right away tells you 3 is cheating. This is not a function. So on your paper, I need you to write NF, not a function. That was really ugly, but it's supposed to be NF, not a function. You'll see that 5 is cheating too. 5 is dating 6 and 5 is dating 8. This is not a functioning relationship. And when you looked at it, or if you were to look at it on a graph, you would see that that X value had multiple Ys. And that'll make sense here in just a moment. So our second one, this is what I mean. And let's see if I can zoom in for you. This is a good example of what I meant when I said it's not a function, it's not a healthy relationship, because let's see if I can get it. Let's see if I can get it right there. Maybe it's gonna work with me. Maybe it is, maybe it's not. All right. So right here, when X is 1, remember these are X's values. These are our X values. When X is 1, if I were to draw a straight vertical line, okay, it would hit here on the 1, and it would hit down here. Okay, if I drew a line all the way through this, it would hit up here and there. That means that the X of 1 is dating Y of 5 and Y of -5. It's dating two different people at the same time. So this circle is not a function either. And you need to write not a function. We also know this as the vertical line test. So if I draw a line here, it hit there and it hit there. If it hits more than once, it's not a function. Down here, oh, let me clear the screen. Clear. All right. And let me zoom back out. See if I can get it to act right. All right. So down here now, we're on number 3. And here, X is 1, dating one person. 3 is dating one person. 5 is dating one person. 7 is dating one person. For every X, there was one Y. This is a function. So you can put an F or you can circle it for function. And on 4, remember, X's come first. And you'll notice on all these, I keep calling these X's. I keep talking about X's first because our definition is for every X, there's one Y. We can't control the other person. It is not doesn't have to be true in reverse. So like on this one here, you see how 6 is a Y. It's dating multiple people. We can't control the other person. We can't worry about it. Our definition is for every X, there's one Y. So when our X was -2, it was dating 3. That's cute. -1 is dating 4. That's cute. Everybody's, it's all cute relationship. So this is a function. So we're going to put F for function. Okay. For every X, there's one Y. So we had two non-functions up top, two functions on the bottom. And on the bottom left corner here, this one is, I need you to draw a cloud. This is inspired by Miss Alanis. If you don't know Miss Alanis, she loves clouds. You know, Mr. Heisen, he's a Philadelphia Eagles fan. I know I'm wearing this cowboy blue right now. It's ironic, but I'm a Philadelphia Eagles fan. That's why I had you put Eagles. This one is a cloud. It's supposed to be like Miss Alanis. She really likes clouds. All right. So our next section, dilations. The meat and potatoes of our test was about transformations, and transformations are a change. There are 4 changes: the dilation, the reflection, the translation, and the rotation. So I'm gonna use purple. So I'm gonna use purple for this one. Dilations change size. So let me actually go back to here. Dilations change size and are always multiplying. Whenever we're talking about dilations, I need you to think multiplication. Multiplying. Bam. So how do they change size? Well, they can increase in size. That means the scale factor is more than one, greater than one, however you want to say that. It can also decrease in size. So we have something that gets bigger and something that gets smaller. That's what a dilation is. As Mr. Heisen gets older and older, I have to wear glasses. And when I go to the doctor, I think it's the optometrist, I believe, ophthalmologist. Ask your mom and and ask me later because I'm gonna look that up. But they dilate your eyes, which means they open up your pupils so they can look down in there and see the back of your eye, and check your vessels in your eye, your nerves, and see what the conditions of your eyes are. Okay, they dilate it, which means they open it up, and then over time it'll reduce. So dilations change size. So they increase, they decrease, and when they decrease, the scale factor is less than one. So right here on your paper, besides writing that in, I also need you to put right here what this is. So 2x, 2y, that is greater than 1. Hopefully you're going to tell me that's an increase in size or an enlargement, ENT. This one here, x and y become half, 1/2 x, 1/2 y. That's a reduction, okay? Now, this one here says 0.1x, 2y. But here the x reduces, but the y increases. So this one right here, I want you to put a mistake, or not mistake slash impossible, because you'll never see that. Okay, that should, I think, was supposed to be 1/2, or I don't know if it was fixed on your paper, but that should have been 1/2. So we're just going to put mistake slash impossible because you can't have a reduction and an enlargement at the same time, at least not at an 8th grade level. All right. And then down here where it's blank, I want you to create your own dilation and then say if it's an enlargement or a reduction, okay? Now with dilations, do we preserve congruence? Congruence means do we remain the same? Congruent, are things congruent? Are they equal? Does this preserve congruence? No, it changes size. So on your paper, I need you to circle no. They do not. Dilations never preserve congruency. Now you can say, well, what if I multiply by 1? Well, it's not a dilation. You're remaining the same. Do they preserve orientation? Orientation is the direction something is facing. So if I have a circle and I get a bigger circle, north is still north, south is still south, east is still, it doesn't change direction. I guess for you guys, I think that's east. I don't know how the camera flips it, but for me, this is east and that's west. So, um, but dilations don't, no matter how big or small I get, that does not change direction. So you would say they do not, I'm sorry, they do preserve orientation. Can I undo that? Probably not. So let me just clear it and recircle. So they preserve congruency? No. Preserve orientation? Yes. Because they remain the same direction. And remember, to preserve something like a fossil or your food is to keep it the same. At the bottom right of this section, we are going to think of Mr. Trevino. So Mr. Trevino is a huge Cowboys fan, so I need you to draw a cowboy blue star right here, corner of your page. Oh my goodness, this looks more like Patrick Star. But cowboy blue star right there. Draw one so we know that you're paying attention in this video, okay? Clearing the screen in 3, 2, 1, bam. Now, reflections. Reflections are always mirroring or flipping the image. You can reflect two different ways. When we talk about reflections, you can reflect over the y-axis, the x-axis, in which case the x values stay the same, or you can reflect over the y values. Reflect over the y-axis, where the y values stay the same. So for example, if the problem said, which one of these algebraic representations shows a reflection over the x-axis, you would say x and y become, x stays the same, but y is opposite. That's why I put that little negative symbol. And then right next to it, put reflect over, or reflection. over x-axis. Here, if it reflects over the y, you can probably guess it by now, y stays the same, but x is opposite. And here, reflection over y. Here, add one more. Either do another reflection over the x or a reflection over the y, but I challenge you to use numbers here. So what I mean by that is maybe you want to put -3 and 6. You should be able to look at this and say then that the original value was 6 because 6 remained the same. Now, you say, well, sir, how do I know the 6 remain the same? That that means over here you would need to put what it originally was. So maybe originally it was 3, 6. Well, if it's 3, 6, like if you showed this to me or Miss Hill, Miss Gray, Mr. Lotto, Mr. Trevino, all the math teachers, if you showed it to us, we would be able to tell you like, hey, that's a reflection of the y because the y value stayed the same and the x went from +3 to -3. So then next to it, you should be putting reflect over the y. That's how we would like for you to do that problem. So just show us that you understand what a reflection is, okay? And now for Miss Gray, this section, we're going to ask that you either write the word flamingo or try to draw a flamingo because Miss Gray loves flamingos. So if y'all want to get Miss Gray a gift, get her a flamingo. I'm going to try to draw me a flamingo right here. All right. That turned out better than I thought it would. So there's our flamingo. That's what I need you to draw in the corner so we know you're paying attention, okay? All right, we only have 2 sections left. Now we're going to talk about translations. A translations slide and are always adding or subtracting. The way you can recognize a translation is if it's adding or subtracting. Bam. That's always like if you see x plus something, y minus something, y plus something, translation has to be. It's the only one that adds and subtracts. So x values are going to go x's. What do we say about x's? We throw our x's to the side, ask God why, or we say x-axis. We do all these songs and dances, but x values, if they're going left, our x values go left if they're negative or if they're subtracting. I won't say negative. I won't use the word subtracting. X values go right if they're adding. Okay. So x's go side to side. Y values go up and down. So y values go up if they're adding, and y values go down if they're subtracting. So looking at our examples here, we have an algebraic rep of x and y become, that little arrows like transforms or changes, becomes x plus 3, y minus 6. You would read that as x, yes, literally as x plus 3, but that means x to the right 3 spaces. Okay. And I'm going to move this out of the way. So this reads as x goes right by 3 spaces and y goes down 6. Okay. For the sake of this video, I am going to format that a little better. Obviously, if you're writing, you can kind of make it look prettier. But now right here, this next one, x and y change or translate. In this case, the translation is x to the left 4. So x goes left 4 and y goes up 6. Okay. That's literally all you have to be able to do with translations. So if you see that on the test, when you do your retest, you see something adding, subtracting, it's a translation, okay? Do they preserve congruency? Well, check this out. Let's do the square. I'm gonna go the side, I'm gonna go side, go north, south. Even if I went diagonal, no matter how I move this, it's still the same size. It's still congruent and it still faces the same direction. This corner, I'm gonna keep my finger on it. No matter where I move it, it still faces that same direction. The corner has not moved. So the direction hasn't changed and the size has not changed. So with your pencil, does it preserve congruence? Yes, it remains the same size. Does it preserve orientation? Yes. Now, perhaps you're noticing that I didn't answer these over there. That's because I was going too fast. So let me go back over here and answer the same questions for reflections. If I had a picture here of this circle, actually, don't let me use circles. Circles are hard. Let me use a triangle. And let me call it ABC. If I take this triangle and I reflect it over the y-axis, or if I reflect it over the x, B, which is at the top, is going to now face down here. This is where B prime is going to be. So B was facing north, but now B is facing south. So its direction changes. It does not preserve orientation, but it does remain the same size. So it preserves congruency, but it does not remain the same direction. My hand faces this way, and it faces down now when I reflect it. Okay. All right. So with translations, for this one, we are doing Miss Hill's favorite. You guys want to get on Miss Hill's good side? Bring her a cookie. That woman loves cookies. She loves milk chocolate cookies. Okay. So draw a cookie. So I'm gonna draw a cookie right here. Mine's because I'm using the color black, it looks more like an asteroid or a moon, but it's supposed to be a chocolate chip cookie. So anyway, draw a cookie on the corner so we know that you're paying attention there. And now rotations. Rotations rotate or turn. Let me pick that. Rotations, I'm gonna use the word turn just so it's more friendly. They turn by 90, 180, or 270 degrees. All right. Rotations turn clockwise or counterclockwise. All right. Each turn on the axis, I'm sorry, each turn through a quadrant is 90 degrees. That's why we say it's 90, 180, or 270. So that means if I took this circle and I moved it here, that would be a 90-degree turn. This first turn would be 90. If I did it again, whoop, that is horrible, but that would be 180. If I did it again, all the way over here, that would be 270, okay? So 90, 180, 270. And then if I went back another 90, be 360, which a 360 is a full spin. All right, so like if I do a turn, I'm like, whew, you just saw a whole lot of fat. But anyway, that would be 360, okay? So we have 90, 180, 270, and 360. But with ours, we're just worried about the first three 90, 180, 270. I can turn to the right and I can turn to the left. Again, if it's flipped on the camera, I apologize, but a wise clock is always right. So whenever you see clockwise, somebody who's wise is right. So clockwise is always right. Counterclockwise is the left. All right. Um, Now, for in terms of our math, when we talk about rotations, they're going to rotate positions if the turn is any version, counterclockwise or clockwise. If it's ever 90 degrees or 270 degrees, they're going to rotate positions. The X and Y are literally going to switch spots. So if I had a 2 and a 4, they're going to go 4, 2 now. Okay. If the rotation is 180 degrees, the values become opposite of what they are. And this is all verbatim and very literal. So For example, 90-degree turn, if I had x and y, that would now become y comma x. If it was 180, it would become opposite of what they are. So it'd be negative x and negative y. If I had 270, once again, the turn would be y x. All right. The one asterisk to all of this, and which I wanted to say for the video, because I didn't know really a better place to put it, and I need you to write this at the bottom of your notes. Take the sign of the quadrant. So, for example, everything I said is fully true, but you need to add the quadrant sign. So, for example, everything here are positives. So if I went 180 degrees, 90, 180, everything down here are negative. It's the opposite of what it was. That's why 180 is just opposite of what it is. But that's true in reverse. So if I had a circle at the bottom where everything is negative, if I was down here and I went 90, 180, everything up here is positive, positive. So if I started with negatives and I moved 90, 180, everything is now positive. It's opposite of what it was. No matter where I start, everything becomes opposite. If I had a positive 4 and a negative 3, I now have a negative 4 and a positive 3. For 90s, whatever it is, they rotate positions, but wherever they land, you take the quadrant, the sign of that quadrant. Typically, you see things from quadrant 1 where everything is positive. So if I was here in quadrant 1, and let's say I had a 90-degree turn here. Well, down here, x's are positive, y's are negative. So whatever numbers I got, let's say I got 2, 1, then it'll be a positive 2 and a negative 1. Okay. Rotations are the hardest, the most confusing, require the most, but it's tested the least. All right. If you know the other three, you should be good. They do preserve congruence. They do preserve congruence. Ooh, that was ugly. They do preserve congruence, but they do not preserve orientation. For this section here, I need you to draw Mr. Lada's favorite vehicle or favorite vehicle brand, the Toyota logo, which is basically a big old oval with a smaller oval up top and another oval going through the middle. Some people say ellipse, but we're just gonna call ovals. We're just gonna call them ovals because it'll be so. Thank you for watching this video. Once you have completed this will be the proof that you understand the concepts. If you've taken that first test and you've watched this, you know a lot of that test was vocabulary. Did you know what congruence meant? Did you know what orientation meant? Do you know what a dilation is? Any problem you're looking at dilations, you know that you're looking for multiplication. If it's a reflection, you're looking for x remaining the same, y is opposite. It's either flipped. If it was a translation, it's adding or subtracting. If it's rotations, they're rotating spots or becoming double negatives. This test was very vocabulary heavy. I think you got it after this video. We'll see. See you in class. And hey, you are loved, valued, cherished, respected, and appreciated. Thank you for spending this time here. Let's have ourselves a great day. Go love on your mom and dad or your grandma, grandpa, whoever you live with. Go show them that you appreciate them while you still can, okay? See y'all in class.